Well, hello there. For a while now, we've been doing an exploration into polar graphs and polar equations. And now we're going to take a closer look at a fundamental relationship or set of fundamental relationships between polar coordinates and rectangular coordinates and their equations as well. And all this is going to stem from one basic diagram that connects everything with polar with everything with rectangular. As we go through, we've got a few examples that we'll go through, and they're relatively quick ones that'll show us how we can go back and forth between polar and rectangular equations. So here's that picture that's so key to understanding what's going on here. So if you remember, in a polar diagram, we're dealing with the circle being the main focus, whereas with rectangular, obviously, we're dealing with rectangles being the main focus of what our graph looks like. So as you can see right here, I've graphed this example function r is equal to 5. And from this, it's nice to see what's going on here. So what we've got is with the polar, we've got r and we've got a theta, right? R being the distance that the point is from the pole, and theta being the angle that's formed between our terminal side of our angle and the polar axis. Well, what we can do is we can draw a triangle up to that point that has an x-coordinate and a y-coordinate that forms the rectangular basis from that. And so this right triangle actually gives us all of our main relationships between r, x, y, and theta. In particular, we know that x is equal to r cosine theta. That's because cosine of theta is x over r, adjacent over hypotenuse. Y is equal to r sine theta. All right, that's because opposite over hypotenuse is y over r, and that gives us sine theta. We know from the fact that it's a right triangle that we get x squared plus y squared is equal to r squared. And then we know just from our basic trig knowledge that tangent of theta is equal to y over x. Now, what that does is it gives us two specific situations that we can deal with in order to figure out what our angle is. And first of all, if x is positive, then we either have a situation where the triangle looks like it does here, or we've got a triangle in the fourth quadrant. All right, and in this case, theta is just equal to the inverse tangent of y over x. However, if you knew that your angle was in the second or the third quadrant, you would know that x is less than 0. Well, how do you take care of that? Because if you remember back from your trig days, inverse tangent only gives us an answer in the first or the fourth quadrants. Well, we take care of that. If we know that x is less than 0, we just add pi to our angle. So what that's going to do is it's going to transfer all of our angles that were in the first quadrant to be in the third quadrant where tangent is also positive. Right? When you add pi, you go to the opposite angle in the opposite quadrant. And then it'll take any angles that were in the fourth quadrant and flip them over into the second quadrant. So if you see that x is less than 0, then we're going to make sure to add pi to get the appropriate angle in our circle. All right, so here's an example here. Let's say, for example, we have the polar coordinate 5, comma 4 pi over 3. How do we convert that into rectangular coordinates? So remember, we have four main ways to convert. And if we're given r and theta, the easiest way to convert into x and y is to note that x is equal to r cosine theta. So x is equal to 5 times cosine of 4 pi over 3. Unit circle happens, and we get negative 5 halves. We also know that y is equal to r sine theta, so y is equal to 5 sine of 4 pi over 3, and so we get negative 5 root 3 over 2. And so our coordinates are negative 5 halves, comma negative 5 root 3 over 2, which we can see right here in our graph. So it's about negative 2.5 and negative 4.333. All right, so those 2 points, r comma theta and x comma y, are equivalent. On the rectangular coordinates for the points with the given polar coordinates, negative 7 comma negative 45. So just a little quick reminder, if we see negative 7 as our r, that means we're going to go in the direction of the angle, but actually backwards. All right, so we would go negative 45 degrees, but backwards from that, which would put us at 135 degrees actually. All right, so conversion actually incorporates all that because all we would do is we would say x is equal to r cosine theta. So x is equal to negative 7 cosine of negative 45 degrees. All right, and cosine of negative 45 degrees is just a positive number. So it's just negative 7 root 2 over 2. On the other hand, with y equals r sine of theta, we can convert and get our y coordinate. So we get y is equal to negative 7 sine of negative 45 degrees, which makes this 7 root 2 over 2 because sine of negative 45 degrees is positive. So we end up with this point, which ends up being negative 4.95 comma 4.95, which is at the same xy coordinate as this r theta coordinate of negative 7 comma negative 45 degrees. All right, so going the other way, find two pair of polar coordinates for each point with the given rectangular coordinates. So -1 comma √3. So how do we go the other way if we're given x and y? Well, first of all, r is the easiest one to find because r is just the square root of x squared plus y squared. So -1 squared plus √3 squared is going to be 4, so the square root of 4 is equal to 2. So we use our formula right here, and we find out r pretty quickly. Theta can be a little bit more of a challenge. So remember, we can find theta by using tangent of theta is equal to y over x, and then finding the correct quadrant. All right, so our second quadrant angle, where tangent of theta is equal to -√3, which is √3 over -1, is 2 pi over 3. So you can remember that from your unit circle. Or if you used inverse tangent of -√3, you would actually get -pi over 3 all the way down here. That's not actually the quadrant that we want to be in because x is negative. So what we would do is we would add pi to that angle, and we would get 2 pi over 3. All right, so the coordinate that we get is 2 comma 2 pi over 3. Now, of course, you can also write that as -2 comma -pi over 3, right, taking into account what we just figured out just a second ago. All right, so many different ways that you can write this coordinate. Let's say instead that you want to have the point 2 comma -4 in our xy coordinates. Can you figure out what's going on with the polar coordinates? Well, r is just the square root of x squared plus y squared, which is 2 squared, plus -4 squared, or the square root of 20, all right, which ends up being about 4.472. However, all right, in order to find out what theta is, we use that tangent of theta is equal to y over x, and we had to figure out the correct quadrant. Now, this is not something that's actually on our unit circle. Tangent of theta is equal to -4 over 2 or -2. So we have to go to our calculator, and when we do that, we get the inverse tangent of -2 is equal to -1.107. All right, so that coordinate is somewhere right about here, 1.107 radians going backwards. All right, so we would write that as √20, -1.017. Okay, so now if we have equations in polar forms, not just coordinates, but full equations, can we actually write those equations either in polar form if we have rectangular, or vice versa? If we have rectangular form, can we write them, or polar form, can we write them in rectangular form? So here I've got x plus 3 squared plus y squared is equal to 9. Well, you convert in the same way that we just did. So there's going to be a little simplifying going on and all that sort of stuff, but we know that x is equal to r cosine theta, so we plug that in for x, and we know that y is equal to r sine of theta. All right, so altogether we get r cosine of theta plus 3 squared plus r sine of theta squared is equal to 9. And then now when you expand, all right, we're going to get r squared cosine squared theta plus that middle term, 6r cosine theta plus 9 plus r squared sine squared theta is equal to 9. And what hopefully you notice is that we get a 9 on either side of the equation. So what I'm going to do is I'm going to group all the terms with an r squared together so that I get an r squared times cosine squared theta plus sine squared theta. The first term and the fourth term here. All right, and I'm going to move the 6r cosine theta over to the right side. So all this is equal to -6r cosine theta. Well, the reason why I did that is because I noticed that I have a cosine squared theta and a sine squared theta. And if I factor in r squared, cosine squared theta plus sine squared theta is just equal to 1. So I get r squared is equal to -6r cosine theta. And then I can divide by an r since we know our r is not equal to 0. And we get r is equal to -6 cosine theta. So if you remember when we were talking about trig graphs, you knew that this polar equation represented a circle with diameter 6 that's oriented towards the left side of what was called the x-axis. So we also notice that this is a circle with a radius of 3. That's the r squared part. The 9 is equal to r squared, centered at -3 comma 0. So it checks out with what we knew before with circles. So now let's try another one. Write the equation in polar form, then identify the graph. So we have 2xy is equal to 3. Again, x is equal to r cosine theta and y is equal to r sine theta. So I'm just going to plug both of those in directly. So now I've got 2 times r cosine theta times r sine theta is equal to 3. When I simplify, I get 2r squared cosine of theta sine theta is equal to 3. And one thing to notice is that 2 cosine theta sine theta is a trig identity. In fact, that's equal to sine of 2 theta. So r squared sine of 2 theta is equal to 3. So if we simplify this a little bit more and solve for r, or r squared in this case, we get r squared is equal to 3 cosecant of 2 theta. So all I did was divide by sine of 2 theta. And in fact, this is a hyperbola. All right, going the other way, write the equation in its rectangular form and then identify its graph. So theta is equal to pi over 6. How can we convert that? So we have two conversions going from polar into rectangular form, either x squared plus y squared is equal to r squared, or tangent of theta is equal to y over x. The more helpful one obviously is going to be the one that involves the theta, the tangent of theta, because that's what we have. We have no r. So what I can do is take the tangent of both sides. So I get tangent of theta is equal to tangent of pi over 6. So tangent of theta we know is y over x, and that's equal to the tangent of pi over 6, which is root 3 over 3. And when I multiply both sides by x, I get y is equal to root 3 over 3 times x. And of course, this is a line that goes to the origin with slope of root 3 over 3. That's the tangent of this graph, of this angle, I should say. All right, so now write the equation in rectangular form and then identify its graph. R is equal to 6 sine of theta. So we got two ways to go back and forth. X squared plus y squared is equal to r squared, or tangent of theta is equal to y over x. All right, I think the easiest way is to notice that we have an r here, and there's one little trick that we can do to make sure that we get an r squared that we can actually use as our way to convert. And the trick is to multiply both sides by r. I know that looks a little counterintuitive, but when I do that, again, r squared is equal to 6r sine of theta. So oftentimes if you're stuck, maybe multiply both sides by r. And the reason why is because I know r squared is equal to x squared plus y squared, and this r sine theta is equal to y. So I get x squared plus y squared is equal to 6y. What I can do is I can move the 6y over to the left side, so I get x squared plus y squared minus 6y. And I'm going to complete the square by adding half of 6 squared to both sides, which is 9. All right, when I add that to both sides, I get x squared plus y minus 3 squared is equal to 9. And so in other words, this is a circle with radius of 3 centered at 0, 3. We already knew that from our trig graphs, right? But now we can confirm that from our rectangular coordinates. Last example here, write rectangular and polar equations for the following graph. All right, so you can see that I got a line that goes through the origin and the point 1, 5. So this is the line y is equal to 5x. Well, how in the world do I convert that? Well, what I can do is I can notice that y is equal to r sine theta and x is equal to r cosine theta. So I get r sine theta is equal to 5r cosine theta. If I divide both sides by an r cosine theta, the r's cancel out, and then we get a sine theta over cosine theta, so tangent of theta is equal to 5. We also could have gotten that by noticing that if I divided by x originally, I get a y over x is equal to 5, and y over x is what tangent of theta is. When I use my calculator, all right, to find out what theta is in the inverse tangent of 5, which is 1.373, or about 78.69 degrees. All right, so from this, we can figure out that we've got two ways of writing this, both rectangular and polar equations. So in summary, there are four main conversions between polar and rectangular coordinates derived from the Pythagorean theorem. And then make sure that you plot the point to confirm that you converted into the right quadrant. And all this can be applied to solving for rectangular or polar equations. Thanks for listening. We'll see you on the next video.